Okay, so before we start, I should inform you a little bit about FECO and Altair. And we still have not got out the license, so you can directly use it at home, for example. It works within the department, but we don't get it outside of the department. So there are two options there. One is that you can download the student license from Altair. You just have to fill out your information at Altair page, and then you can download it and run it on your own laptop. And the other version is that we can use remote desktop. So you have to be within Lund University or use your VPN connection. And then you can connect to the computers in room 4118 and 4119. The names of those computers are on the Canvas page. So in that way, you can actually access Altair and FECO from home, but over remote desktop. And of course, you're very welcome to come to the lab rooms where we have Altair installed, and you can run it on those computers. So that is the solution that we have at the moment for being able to run the lab starting later this week, and also to do the computer lab or exercise that we have on Wednesday. And I think that will actually work in that way. Has anybody of you been to 4118 or 19 and tried Altair?
Yes, I have been there.
Did it work?
Yeah, it worked.
Well, very good.
Yeah.
So that's really an option for all of you. And I think the instructions we have of it should be quite self-explanatory. So you can actually run it with those. But of course, on Wednesday, you have the time to do it in a proper way. So try that for all of you. And definitely also, if you don't want to go there, either download the student license or try this VPN connection. There is, of course, a chance when you try the VPN that somebody is running on that computer, because students can sit there and you cannot kick them out if they are running on the computer. But I think we will get that to work. And on Wednesday, that room is reserved for you. So then you are the only one who should be there. So I hope that will actually work for you. Okay, any questions about Altair and FECO, or the computer part of this course before we start? Okay, otherwise we will then move on to this patch antenna. So that will be what I see as your new favorite antenna. So we had the dipole, we talked a lot about the dipole. Now we will move on to this patch or microstrip antenna. And of course, this is the antenna that you will also, build yourself. So you will make this antenna. Okay, so today what we will do is to cover this patch antennas, in general, a little bit about antennas above a ground plane, talk about what is the patch antenna, dielectric substrates, how we can feed it, basic techniques to analyze it, the radiation resistance, and the radiation patterns for it. And then in the end of this, I will come to this laboratory session that starts now. So really talk what you're going to do in the lab, and we're going to form the lab groups also if you have not formed it already. So a patch antenna is an antenna above a ground plane. And last week we started to look on antennas above a ground plane. And particularly we look at these so-called monopole antennas. So these antennas here that looks like this one. So in some ways it's an antenna where the current is vertical compared to the ground plane. So it's really this current that we have up here, this type of vertical current. That is the direction of the current we have, because the current goes here on this monopole. So the way we learn to analyze this and understand this monopole is that we formed an image current. So we remove the ground plane, and then when we removed it, we had to add this image current. And the image current have the same direction as the current on the monopole. And that means that the monopole in some ways becomes dipole. So if you think about this dipole current where you have this cosine shape, so a lot of amplitude in the center and then going to zero at the edges, that is what we will have on the monopole, but only half of it. And then the radiation that we have to add the part which gets reflected in the ground plane, and it looks like that comes from the image current, which means it's a radiation from a dipole. The main radiation of this, if we think about the radiation pattern of this, that is then the radiation pattern of the dipole, and then if I have it here, it's this donut type shape that comes out. So it's really radiating maximum here along the ground plane. If you think about the typical use of this, you can put them on Earth and an antenna sticking up, and then it will cover the people who are on Earth because it will follow the ground, which is good because most people are on the ground. They are not up in an airplane. So it's pretty good for these kind of cases. We saw also last week that sometimes it can be problematic because it's sticking out quite a lot. So the height that we have in these cases, the height of this monopole is quite high. We typically would like it to be quarter of a wavelength, so lambda over 4, which is then the lambda over 2 dipole. So this is the typical half wavelength dipole because we removed the bottom part. So we gain a factor of 2. And then we also learned this technique that, for example, we can do these meander lines and so on. They also work well for monopole type antennas. And then we can shrink the height. So we can get them down to, I would say, something like lambda over 20, which is quite a good. I mean, you can push them down quite a lot. But of course, in some cases, this is not enough. You would like to have something that's even closer to the ground plane. If we think about these cases, take like 1 gigahertz, and then 1 gigahertz lambda is 0.3 meters, which means that lambda over 20 is 1.5 centimeters. Not too bad, but still it's sticking out quite a lot. And of course, if you go to even lower frequencies, it's sticking out more. So you would like to push it even closer to the ground plane. You can think about some cases you would like to put it really on the ground plane. The next thing you could think that you would like to have is radiation out from the ground plane. So if I take this again, I had this vertical one, then I had this radiation pattern. Imagine I would like this radiation pattern instead. I would like it to radiate like straight out. If you think that your antenna sits on Earth, probably not what you want in most cases, because then you radiate to satellite or you radiate to an airplane. But if it sits on the side of a house, if it sits on your clothing, yeah, maybe you would like it to radiate away from you in some ways. So in many cases, you would like to have that type of radiation. And that you cannot do with monopoles or these vertical currents. You need to do something else, typically horizontal currents. So if we look at this horizontal current, then we sit in a different version here, because the horizontal current, say it's like this direction, then the image current here goes in the opposite direction. So in some ways, they cancel each other if they are very close. So you get this short circuit version if H is approximately 0. So they are not that good either for this case of just directly thinking of radiation straight out. We will actually soon see this is what we use, and that is what we perform with the patch antenna. If we were doing it with a dipole, what we would need in these cases for a constructive interference is that this part here is lambda over 4. So if you have a height of horizontal dipole, you put it quarter of a wavelength above the ground plane, you actually get constructive interference in this direction straight up. And you will get this radiation out from the ground plane. We will see that a little bit later in the course, especially when we come to array antennas. That is the constructive interference. So we need to do something slightly different here. So we can now introduce new antennas, and that's of course what we will do with the patch antenna. And we can ask the question here, how we can really design antennas here, which have a very low profile and radiate out from the ground plane, because that's what we would like to have. You can see it from many applications. Think about, you have your body. You, for example, can put antennas on your body. You don't want them to radiate into your body. You want them to radiate out from the body. And you don't want them to stick out. You don't want to walk around here with an antenna sticking out from you. You would like to put it basically inside of your clothing. And the same thing if you think about some cases like a car, airplane, and so on. In many cases, we would like to put antennas in the hull of it. So if you have a structure, you would basically like to have it on that surface already and not protruding out from the surface. So this is the antennas we will now study in today's lecture, because that will be our patch antenna. So if we go to our patch antenna, it can look in many different ways. This is a typical picture of a patch antenna. I have the same antenna here. It can be hard to see, maybe the picture is very small there. And what's sitting in these cases is some type of metal. So here we have in these cases a rectangular shape, and that is the metallic part of it. But there is also a huge amount of metal down here, and that is the ground plane. So it's sitting above a different ground. And in some cases, this ground is large and sometimes it's small, but it's really sticking out everywhere below these ones. The shape of these ones are in most cases rectangular. There are also circular versions of this and other shapes. You can do any shape. In this course, we will focus mainly on this rectangular one because it's the simplest one to make, it's the simplest one to analyze, and it's the most common one. If you take a typical patch and you would just pick one, it will be a rectangular patch. It's the most common one. Circular polarized ones or circular patch antennas comes in when you want circular polarization, which we will also talk a little bit about later. So that is a polarization direction that is changing, in some sense, it's rotating around. We'll come back to it. And the good part of this one is that we get the radiation we would like to have. So here we have now the radiation pattern of it. So it typically radiates away from the ground plane. Precisely what I said we wanted to have. So this is a good type of radiation. It occupies a very low profile. Maybe in the one you see here, maybe you can think this one is quite thick, and this is a very thick patch, unusually thick patch. This is the patch antenna you will make yourself. Now you see it in front. If I put it on the side like this, maybe you can see how thin it is. It's like 1 millimeter of thickness, which means that you could put this on your clothing like this and it doesn't stick out. Of course, in this case, it's stiff, so it's not so comfortable to carry around, but you can make them soft. You can actually stitch these type of antennas. So you can put them inside of your clothing and still make them work quite well. So very, very low profile. So the H that we have there, the height, can be much smaller than the wavelengths. It can really be a small fraction of it, like a % of it. A really, really tiny piece of the wavelengths that you have. And it's then conformal to surfaces. So in these cases, of course, these are planar. The one you will make will be a planar patch antenna. But you could think about these could be a little bit soft, so they can turn around if you bend your body and so on. So you can really shape them also according to the surface if you would like to. It's extremely simple and inexpensive. And one reason for this is that the manufacturing of this can be done with technology which is very similar to printed circuit boards. So the typical way that you print electronics, in the same process you can print these patch antennas. Because when you print your electronics, in most cases you have this ground plane here. So that is one metallized surface. Then you have some material that sits here, that is this dielectric substrate. You will use a substrate called FR4. It's like a plastic material. And on top of it, up here, you also have metal. And then you take some technology and you remove that metal. What is then left is the metal that you do not remove, which, for example, could form this patch that sits there. And then you can do a lot of things like this. So extremely simple, extremely good and easy to produce. Good antennas. When you build it, you can also build a feeding network. So if you see this one here you would have your patch, here you would have a feed of it, and you can see that you can get a signal to travel along these lines. And those you can produce in the same way as you produce the patch antenna. It's just that you leave metals also there. So this is called microstrip lines. And that is also, in a way, it's almost together with the manufacturing of this patch antenna. And a different name of it is actually microstrip antennas. So instead of patch antennas, they go also under microstrip antennas, because these lines on these printed circuit boards are microstrips. So you can do that. And the version I showed you here is what's called an array. We haven't come into arrays so far in this course. We will do it next week. We'll start with array antennas. And array antennas are antenna elements put next to each other. So this version here will be a 4-element patch array. So that's one array antenna, still with only a single feed here, but it starts to form an array antenna. And you can do this easily also with patch antennas. So they have many, many good properties here. And then you can ask how you manufacture these ones. And there are different technologies. The most common one, and especially traditionally most common one, and the one we used in this course until approximately 5 years ago, was something called etching or photolithography that you have up here. So that is a technique that in the lab, you, as the one who's taking the course, actually produce an A4 paper, and on that A4 paper you printed here a rectangle and a little dot. And what we did is that we put this into a machine and removed the metal outside of that one. And that you can do by illuminating these ones with special light, and you use some chemicals. The chemical in here can remove the metal. So in the beginning, there are metal all over this place, like copper. And then by having illuminated some part, you can save that from this chemical process. And then the metal there would stay, the rest will be removed. And that is the reason when this was drawn, you basically made this entire black here, and that is what we kept. And then afterwards, you can solder here an SMA connector to your patch, and that you will also get to your patch. And then you could get an antenna that basically looks like here from the back. That's SMA connector. And in the front, this is the new version that you will make. And those, we actually use the laser-based technology instead. So that is a version which is much better than this chemical version, because it can make finer pieces and so on. And it's in some ways quicker, at least in some aspects it can be quicker, especially for small regions. And here you can have a almost like a high power laser that burns down on the copper, and then in some ways the heat evaporates the copper, and then you remove copper from this piece too. There are some movies you can see on this if you press on these links that sits inside of this lecture notes. And you can see this running around over this piece, removing the copper and make a very, very fine print. So these are standard technologies to make electronics, and of course to make these type of antennas. They always sit here on what's called a dielectric substrate. So this type of plastic type material, which you build it on. The one that you will use here in the lab is called FR4. It's the most common version of this. It stands for flame retardant material. And there are many other types of materials. For antennas, in most cases, you want the material with the lowest losses, and then you can have other materials with lower losses in some ways. I think I got a question on the chat here, while we need the dielectric surface here. If you didn't have the dielectric, look at this now, this very thick patch. What would happen then? I have a ground plane here, I have the patch here, and of course then I would have a patch floating in air. And it wouldn't have any mechanical stability. So to make it stable, this metal here cannot float in air. It needs to sit on something. And what it sits on is this plastic material. So it really supplies these mechanical properties to it. Copper cannot just float in air above a ground plane. Something needs to support the copper. And it can be different materials. Most common ones are this, like FR4, Teflon type materials, and many other types of materials. We will talk about their properties very soon. So that's why you need to have this dielectric material. And there's of course a lot of work that try to make that dielectric material good, in the meaning that it should be good for antennas. So that means now we have a dielectric substrate. And as I just mentioned, it's a mechanical support for the patch. It's used in all printed circuit technology. So it really is something like this, sits like that. It sits inside of this. It's the way it is made in some ways. You could think about today, we could start using 3D printing, and it can be done for some of these cases. It's a very popular new ideas to make different geometries in a cheap and efficient way. Printed circuit technology is, I mean, in many cases, superior when it fits. But of course, it can do like 2D things. Then you have to layer those, but you cannot do pure 3D things in some ways. For antennas, they should have low loss. So we would really like to have as low losses as possible because we don't want to waste energy into heating of the substrate. And now comes then the question, what happens when I put a dielectric into my antennas? And the major effect of having a dielectric inside of your antennas or your electromagnetic fields is that we start changing here the wavelengths. So if we think this first top up here, that is in vacuum or air. Vacuum and air are almost the same in the properties here. They differ in the 5th or 6th digit here. So we can say vacuum or air is the same, epsilon r equal to 1. And this is the case where you then have a simple relationship with your lambda and the speed of light in vacuum. But when you put your wave into a dielectric with a higher permittivity, you change the refractive index. So this is epsilon equal to 2 and epsilon equal to 4. And what you can see here is that the wavelengths now starts to differ. So here you have a different wavelengths. And in the bottom one here, you have an even shorter wavelengths. And the wavelengths here scales with the refractive index of this material, which is proportional to the square root of the permittivity. So you have a shorter wavelengths inside of the dielectric material. And you have learned something about antennas. And what is the main thing we learn about size of typical antennas, like the dipole? It was that it should be half a wavelength. And now if you put your antenna in a dielectric, of course, maybe it should be then half a wavelength inside of the dielectric. So you have to compensate here what the wavelength is. The wavelengths that actually the antenna is experience for this electromagnetic field. That is what we will need to use. So the relative permittivity, if you have not seen it before, it is a material property that describes how the electromagnetic waves are interacting in this material. And it is related to a parameter that I think you've seen in, for example, some physics courses and so on, the index of refraction. And that is the square root of the permittivity or the square root of the relative permittivity. In these cases now, I assume that there is no magnetic materials. In most cases, there is no magnetic effects. It could be, but we skip them in this course. And that means that the wavelengths here, so if I take my epsilon inside of the material, so epsilon, epsilon, that is then related here to the free space wavelengths divided by the square root of the permittivity, relative permittivity, which is the same here as you can say, you can write it as the speed of light divided by the refractive index, that is the speed inside of this dielectric material, and then normalize with the frequency. So this is the effect we get by having this dielectric. We change the wavelengths. And as wavelengths is the most important parameter for the antenna, it's important. Of course, this will come into our patch antennas. We have to compensate for this. Okay, so then we know something. We know something about this dielectric substrate. It changed the wavelengths of it. So that will come into the resonance condition. And then we should, of course, feed this. If we think about the dipole, we just say, let's feed it in the center. We didn't really go into detail how we did it. We talked a little bit about connectors and so on. Here we will use this SMA connector that we looked at I think it was 2 lectures ago, or it was last lecture. And patch antennas can be fed in many different ways. The most common ones is the one that we can see here. It's called a microstrip feed. So it's a microstrip line that connects to your patch. So it means that the wave is coming here. Somewhere it's excited on the microstrip. And then the wave is traveling on the microstrip, basically below the microstrip, the main intensity. And then it reads the patch, and then it's trying to be resonant on that one, and then it tries to radiate. And if we think about the production of this and this printed circuit technology, these are, of course, very easy to fabricate because it's the same technology there. Then you can ask, how should I excite the microstrip? And maybe there you will need a coaxial cable and then do what we do directly in the next one. And that's to use a coaxial line, which is also easy to fabricate. And in this case, we have a coaxial line, so the signal is coming from below. It's coming underneath the ground plane, which is what you have here. This is the patch antenna you will build. And here is the connector to that one. And then it's sticking up. So the the exterior connector goes to the ground plane. And the inner connector sticks up here and reaches the patch somewhere. So you have some feed points sitting somewhere here. So that is where this comes up to the patch. And these are also pretty simple to fabricate. We will give you one that is prefabricated that we will give to you. What you have to do is then to add your patch above it. So we will add this inner piece, if you can see it here. And then to make it larger, you add metal outside here. We give it to you, like aluminum tape or copper tape. And you do that in the size you should have it. You place it on the correct place, and then you actually have built your patch antenna. There are other versions. There are, for example, aperture coupled feeds, slightly more advanced. We will not go through them in this course. There is proximity coupled feeds, and there are actually more down here. So there are different versions to feed this, and we can see those as more advanced versions, which are good in some cases. The basic ideas of understanding the patch antenna you will get in this course, and we will mainly look at this one. This is the one we will focus on, because this is the one that you will actually build yourself. So we use the coaxial line feed in the course. And now we need to then understand our patch antenna. So we need to analyze what is happening with the patch antenna. So if we think we will do as we did with the dipole, we will figure out some simple models and actually show that they work well and that we understand those models. And the models that comes out in those two basic methods here, these are the two most common ones. They are either called this transmission line model or the cavity model. They are slightly different, but in most cases, they're actually very, very similar. The transmission line model is very good if you're an expert on transmission line, which most of you are not. The cavity model, I would say, is easier to understand, and that is the one that we will focus on this course. So we will look at the cavity model to analyze the patch antenna. So what the models do is that they provide this basic understanding. So really the fundamental understanding of how your patch antenna works. And it will give you design guidelines. So when you start designing your patch antenna, you will get the idea of how big should it be from these models. And then afterwards, it's very important here that you do full wave simulations to improve the design. And that you do, of course, before you manufacture it. And afterwards, you manufacture it, and you might have to then fix it in some ways. And you will use FECO to do your full wave simulation of your patch antenna to make it slightly better than the cavity model. And in these cases, we should say, of course, there are improved formulas of this that can be used. But when you have a simulation software, they are not as useful in some ways. So now we need to do our cavity model. And the cavity model is based on understanding of what the electric field is below your patch antenna. So if we think what actually is happening here, we can look at the simulation. So what we see in the bottom piece here, we can see a simulation of the electric field under your patch. And what you basically can see is like pumping upside down. So one is high, one is low, which means that on one side it points like this, and in the other side it points like this. This is the electric field in the Z direction. And then they are flipping order in some ways. And in the center, the field is very weak. And this is the solution we actually get if we solve the electromagnetic problem by some boundary conditions. And if we look at this, what we will say that we have here is the top part and the bottom part. This is a good metal. So on top of your patch, metal there, metal there. Say this is now a perfectly electric conductor, which means that the electric field has no tangential components up there. And what you can think is happening, it's a good conductor, so this means there is a short circuit of this. And that is what's happening then, top, bottom. And then you can ask what's happening on the sides of this patch. And there it's the opposite, there is no metal at all. And what we do is that we model that with its opposite version of material, which is called perfectly magnetic conducting, which instead say that the magnetic field vanished there. In a transmission line, this will be an open circuit. So if we add that on the other sides, we actually have a problem where we know all the boundary conditions, and then we can plug in Maxwell's equations. And we can solve Maxwell's equations for this case. We can ask what kind of electromagnetic fields can exist inside of this cavity. And that is done in the appendix. So I will not go through that here, but you can take a look at it. And you can actually see that the solution to the Maxwell's equations in this case can be written like this. So here, we actually have what the electric and magnetic fields are. This is the lowest order mode underneath this patch, which is used by the patch antenna. And what you can see here is that the electric field, it has an amplitude, plus or minus here doesn't matter. It's oscillating up and down anyway, as you see down here. And then it has a shape that comes in from this sine function here. And in the middle of the patch, there x is equal to 0. Then sine is very small. That is in here. So here we can see the electric field. So this is the place where x is 0. And then on the edges, x is equal to L over 2. And then sine pi x over L is equal to 1. And that's the amplitude we see down there, and we can see it up there. So the electric field is very weak in the center of the patch, and it's very large at the edge. And that is now in one direction. And this is the direction I call x here. So that is the x direction. And then if we go in this direction here, this we call y, we can see this is independent of y. There is no dependence on y. So it's constant when I move it over y. That is the solution that we have. So this is what the electric field is in this case. And the relationship with this one is then related to the impedance of the material that we have. So the dielectric constant that comes in there. And for this to really be a solution, there is one more requirement. And that is that there is a relationship between the wavelengths that we have and the length. And that relationship here is here. It says that the length of the patch is lambda over 2. So this is the requirement that we have. And now it is lambda epsilon here. So it's lambda in the substrate, which means that it is the free space lambda over 2 and square root of epsilon. So half a wavelength in the substrate. Isn't it amazing? Remember your dipole. It should be half a wavelength long. We had a little bit to argue, basically we have to claim it is half a wavelength, so we have to say we know it is half a wavelength. Suddenly here, we can actually solve Maxwell's equations. And Maxwell's equation says it should be half a wavelength for this ideal case of the cavity model. We will see with the dipole, it's just a model, and the real length is slightly off from this. But this comes from this modeling of the patch as a cavity. In reality, of course, it's not exactly a cavity, but it's a very good model for these cases. So that means that we can now start designing our antenna. And what we have to do is then to adjust, for example, the radiation resistance. We know how long it should be now, half a wavelength. We would also like the antenna to be 50 ohm. So how do we make it 50 ohm? We do that by placement of the feed. So where should we feed these ones? So for example, I can put the feed in the center. Extremely bad idea for a patch antenna. I should do it off center. So maybe I should put the feed out there. And the question is, of course, where should I precisely put it? So what is then the distance out here? The distance in this case is from the center to the feed point. How far away should I put it to make it 50 ohm? And imagine you will build your patch antenna. You will build this one. I mean, you need to put it on the right place. Otherwise, it's not 50 ohm. So we need to analyze this. And then we start asking, okay, what do we know about this case? I put a feed here, which means that in the feed here, I really have in some ways a voltage that sits there. So I have some voltage between the patch and the ground. And that I can actually write with the electric field. And the electric field is volts per meter. Simplest model, multiply it with the height. So the height of the patch that sits here is h that I have here. So I multiply h with electric field per meter, I get the voltage. And of course, I have the x dependence from the shape of the electric field. So this is how the voltage looks like. Then I can ask, what is the radiated power? And the radiated power, we assume it's a low loss or lossless antenna. That is the voltage times the current in the feed over 2, the real part. I rewrite that in the voltage squared over the input impedance, complex conjugate. Now I assumed it's a self-resonant patch here. So the input impedance is resistive. And that means here that the radiated power of these ones can be written as the voltage squared over 2 times the radiation resistance. So that is what your radiated power is. That is something that we know. And then we know how that changes when we move over the patch. So the radiation resistance of these ones, I can just flip around the equations here. And then I can write up here, what is the radiation resistance? So the radiation resistance now depends on a few parameters that we have here. H, E0, and 2 times radiated power. And of course, you connect your antenna, yeah, probably the thickness, you know, the electric field, you don't know. The total radiated power, you don't know. So how should you use this? The key thing is that you know the important part, and that is the shape. So this one depends on the shape factor, which is sine squared times x and pi over L. So it has this shape here. It has this shape. That's how it looks. That is how the radiation resistance looks. And now what I did is that I normalized it with the radiation resistance at the edge of the patch. And then we could think, let's measure the radiation resistance at the edge. You could do it. It's not a very good idea. Just measure it somewhere else. And then determine the normalized here radiation resistance. It means that there is some constant that you don't know, times the sine function. You know what this one is, you know L, you know this one. It means that you can actually calculate this one. So that you can do from any position. And then you can use that formula one more time to determine where you should put it to get 50. And then you have a design rule for designing your antenna to be self-resonant, half a wavelength, and placement of your feed to make it 50. This you are going to use in your lab. This is in some ways the most important formula that you have for your patch antenna, together with this L/2 length in some ways. That is the formula. So this formula here is extremely important for you. So you should, of course, really understand that one. And it's a fairly simple formula. You should also understand where it comes from. So these things up here with this cavity model and the distribution of the electric field under the patch, because that's where you get it. So that was the cavity model. And the cavity model is, of course, an approximation. So we did really make assumptions here. And we did the assumptions in these cases that the electric field only lives here. And of course, then you can ask the question, is this a good assumption? No, because it would mean that outside here, the electric field is zero, that it is in the cavity model, which means it's not a radiating antenna. In reality, you will get some leakage outside here. So outside here, the electric field is not zero. And this is what's causing the radiation. So you have something that's called fringing fields. And that's, of course, perturb this cavity model a little bit, a few %. So it is a model which is extremely good, it's extremely accurate, but of course it's not exact, even if it solves Maxwell's equations, because we have made simplifications when we do the modeling. So the resonance here is often just below λ/2. Remember something, your dipole? Is it resonant for half a wavelength? No, it's not. It's resonant slightly below. Your patch antenna is not resonant when it's half a wavelength. It's typically slightly below. But it's a rule of thumb that you can start with. And then you can put it into FECO and you can improve it. So you feed it off center to then increase the radiation resistance to the number you would like to have. And you adjust it according to this cavity model. That is the formula you will adjust your positioning of your feed. And then you use full wave simulations to improve the design. And then you use measurements to finalize the design. So in the lab, starting this week, what you will do is actually you start with this. You start with your λ/2. That is paper and pen formulations. That is your first design step. Then you do these full wave simulations that you do also starting this week. You simulate your patch and you improve the design. And then on the first RF lab, you would do measurements to actually adjust it so it becomes 50 ohm and it's self-resonant and the desired frequencies. So you will do this entire step in this course. And now we will ask some questions here. So how should you actually move the position of it? How should you adjust the position? So assume now you sit in the lab, and this is what you have done. You determine the radiation resistance to 100 ohms for a self-resonant patch antenna. That you do by measurement. So you plug this into a VNA. The VNA determines the reflection coefficient. You make sure it's self-resonant, your patch, it should be. And then you look at what is the radiation resistance. Let's assume you measure it to 100 ohms. And then what you're going to do, that is that you're going to change your feed position. So you're going to move the feed. So for example, here you could say that I had a feed placed here. The question is, should you now move the feed this direction or should you move it this direction? How should you move the position of the feed to make it 50 ohm? So the options here is A, you move it towards the center, which means that you moved it in this direction. You move it away from the center towards the edge. That is this one here. You randomly pick a new point. So probably not a good option. It happens sometimes that people do it. And D, of course, you use a cavity model to calculate the new feed distance. And of course, there can be more than one that is correct of this. So let's make that as a poll for these cases. So again, A, move it in the center, B, towards the edge, C, randomly, and D, use the cavity model to calculate it. So what do you say? How do you do it? You will do this week in your lab when you start designing it. You will do it in the lab when you measure it, week 5, I think it is. So what are you going to do? How are you going to change it? And of course, how do we know that from what I've been talking about in these formulas? So 50% has voted, a few more votes. Okay, I will close it in 2 seconds. Last votes. Okay, let's end the poll here. So this is what we got in these cases. I don't know if this market D should be the correct one. In this case, both A and D are the correct ones, which most of you had. So that is what you should do. The random pick and see, yeah, some people do it. It's not really a good way. Eventually you will of course find it, but it takes a long time. And in the lab, you manually actually have to change your aluminium or copper tape that you use. It's very time consuming and not that fun to do. So why is then A and C correct in these cases? So what did you have in this situation? You had 100 ohms. That is what you measured. So you measured your 100 ohms in these cases. You get these ones. So you should get 50 ohm. So you should lower your radiation resistance. And then just look at the formula here. The radiation resistance, if you put it in the center, so I put it here, that means X equal to 0. What is then this equal to? That's equal to 0. So it's really low in the center. There is nothing there, because the voltage is 0 at the center in this model, which means the radiation resistance is 0 for this case. So not a good idea to move it in the center, but you should move it towards the center because you should make it lower. If you move it towards the edge, you make it higher. So think about this here. The electric field is of course stronger at the edge. So radiation resistance increases when you go to the edge. And to really calculate the one, yeah, you can use this one. So you can plug it into your cavity model. It will also require here that you know where you had your original feed, but that of course you always know, because you have a feed position, and that is your X. And by doing that, you know X, you know this one, you know L that sits there, which means that you can actually determine this thing. And when you have determined that, you know what you would like to have, which is 50 ohm, and then you can calculate X again. So you can invert that one and calculate X. And then you actually figure out what position you should use. And that's also what you would use in the lab and when you build your antenna. Okay, so with that, we will take a break until 1/4 past, and then we'll continue with this patch antenna for these cases.